In the course notes, we've derived a variational form of Maxwell's equations that only involve the magnetic field. The question is, if you start from a solution to that particular variational problem, so the one involving the magnetic field, can you transform then these equations into an equation over here that only involves the electric field? So this is not a completely general way of showing that this particular variational form here is the correct one for the electric field. It's just a way that starts from the assumption that we already have a solution for the one involving the magnetic field. So just to jog your memory, the variational form for the magnetic field that we're going to use can be found in the notes and is the following. So this J is 1 over the scalar product of H with itself. And then we have the volume integral of 1 over epsilon. Epsilon, again, a function of the spatial coordinates. And then we have the curl of the magnetic field, modulus squared, dV. So let's try and think about what it means to have a solution to this particular equation and to Maxwell's equations, see what that means, and then use that information to transform this equation over here into that equation over there. So pause the video and see if you can figure this one out. Obviously, our solution should satisfy Maxwell's equations, so these will come in handy. So first of all, we have the curl of the electric field is minus j omega mu h. And just because I'm lazy here, I will not explicitly mention that this depends on the spatial coordinates. I will also not write the vector signs, just to speed things up a little bit. And then we also have for the magnetic field a similar equation, j omega epsilon e. So these equations we have, and then obviously we also have that equation over there, that you should have a solution to that equation, a field profile that minimizes this variational form. Let's just write it in a slightly different format here. So just copying the numerator. So curl of h squared dv, but let's explicitly write down what the denominator is here. That's the integral of the modulus of h squared dv. So obviously, if we have a field distribution H that minimizes this variational form, then what this thing should give us is the eigenvalue. So if we have a solution, and that's a big if we have a solution, then this thing is equal to omega squared mu. So that's only if we have a solution. Okay, these are the things we're going to work with. Pause the video and use this information to go from here to there. Let's try and get rid of the magnetic field, shall we? So let's first of all look at the magnetic field over here. That is the curl modulus squared of the magnetic field. Now, if we look at this particular equation over here, we will be able to quickly realize that this is equal to omega epsilon e squared. Now, our omega squared, since we have a solution, this omega squared will be equal to j divided by mu. So this is j divided by mu. And then our modulus of epsilon squared, we're going to assume that we're working with lossless materials. So if epsilon is real, so that's the assumption here, then we can just bring that out of the modulus sign, and then we get this equation over here. So that's the numerator taken care of, gotten rid of h and translated that into the electric fields. Let's do something similar for the denominator. There we have the modulus of h squared. So now we need to look at this particular equation over here to transform that. So this will become the curl of E divided by omega mu, and then the whole thing modulus squared. Now let's have a look at 1 over omega squared that we will have. So 1 over omega squared, this will be equal to mu divided by j. So mu divided by j. And then we just have the curl of E squared divided by mu squared. So curl of E squared, and then we just have a single mu in the denominator. This could be a good time to pause if you didn't end up here by yourself. So just pause the video, substitute this thing into that expression over here, there, getting rid of the magnetic fields everywhere. Okay, let's get started. So let's write down our variational form, J. And first of all, we're going to rewrite the numerator. So the numerator, that's this thing over here. And we're going to substitute what we found over there. So for the numerator, we have a volume integral of 1 over epsilon. And then we figured out that here we should write J over mu epsilon squared magnitude of E squared dV. That's the numerator. And then the denominator. Okay, for the denominator, we had h squared, and h squared is just this thing over there. So that will give us the curl of E squared divided by J mu. Now comes the fun part. Let's get rid of this mu. Let's also get rid of an epsilon over here. What else? We can get rid of a j over there. So finally, we can rewrite that expression. If we just bring the denominator here to the left-hand side, we have that 1 over j, and then the volume integral, I forgot my dv here, the volume integral of the curl of E squared dv is equal to, and then for the right-hand side, we have the volume integral. We have 1 epsilon left, so that's epsilon magnitude E squared dV. And that's precisely what we needed to show. We just bring this thing to the right-hand side, and then you see what we needed to show indeed is that the curl comes in the numerator and the epsilon E comes in the denominator. So we have the volume integral of curl of E squared dV divided by volume integral epsilon E squared dV. So there we have it. Again, this is not a general proof that this is the correct variational form for the electric field, because we really started from the assumption here, and specifically at this particular point over there, that we started from a solution to a similar expression involving the magnetic field. But in another exercise, we'll make this more general.